Right about now, a long way away from where I am, there's a mining truck that belongs to Fortescue. It's in Australia. It's moving for the first time under electric power, powered by a humongous battery pack. It's going to help transform the mining industry by doing away with the big diesel electric hybrid setups of old mining trucks and usher in a new all-electric world where mines have low carbon emissions or lower carbon emissions. And it all starts here, at least for the Fortescue trucks. It starts here at WAE Technology, here just outside Oxford, England. This is a video that I recorded a while back, but you may have seen the other videos, that the tour of the facility, the new technology that's being developed to make battery packs last longer, charge faster, go further. But now we're going to talk about the big battery pack. 1.4 megawatt hours of battery packs. And there's no better person to talk about it with than Alec, Patterson.
I'm the program manager for WAE Technologies, and my job role in this is effectively to work with the engineering team here at WAE and put together these huge batteries, as you call them. Should I give you a little bit of background into
I would love
how
to
they're built
know.
up?
So, I mean, obviously, battery packs all start off the same way, right?
Yes.
You have cells, you build them up into modules, or in the new modern designs, cell to pack, and then you eventually chain those batteries together in different configurations, series and parallel, and you end up with something like this. But how do you start building a battery pack that's designed to move a mining truck?
Okay, so first things first, you have to see whether it's physically possible. And that's where our simulation team come into it. Before we've even designed anything or started with the cell selection or anything like that, we look at, is it physically possible? So we have a battery simulation team here that can do some calculations around the amount of energy we can extract out of cells and then modules and batteries, as you mentioned. And we look at a typical mining haul route profile, and we're able to, sort of using our simulation tools that we've developed through our work in motorsport and in automotive as well, we're able to then be able to sort of conjure up how a battery would perform in that environment, and we're looking there about how much would a truck go uphill, and then with a load effectively, how much it will go downhill regenerating the battery, what size therefore would a battery need to be in order for this truck then to operate for a certain number of hours on the mine site between charging. We're able to do all of that digitally before eventually we're able to say, right, a battery pack of a specific size would be perfect for that truck. Once we've got that data, we then hand that over to the engineering team, and we effectively say, right, the cells that we suggest we use, we're always looking for the most optimized cell that's out in the market. We're currently, as a business, we're always working with the best cell providers around the world, and we're in constant dialogue with them to understand what their technology roadmap is for the future. We're able to then take that data and then say, actually, for the space frame that we've got, because obviously we've got a limited space within the truck, we're able to make a battery effectively that comes together at about 1.4 megawatt hours. We do all of that in a concept phase. And then we turn around to ourselves and say, yes, we've got ourselves a project here. And we came back after, we do all that in about 6 to 8 weeks. We came back to Fortescue Mining Group and said, we think it's physically possible. We think we can get a 1.4 megawatt hour battery pack within the truck. We're using a Terex MT4400 truck as our sort of mule vehicle, if you like. And as you said before, that's getting stripped and it's getting rebuilt with our battery packs today. But if I take you back to how we built this, which would have been about 18 months ago, we built our first sub pack. What we do is we take the cell, we then sort of try to understand how we're going to build that into a module and build that module up. And each time we build the module up, you're actually increasing the voltage. We need these battery packs to be working at 1400 volts, which is the voltage levels that the inverter and motors that are already fitted on the truck work at. So that for us is a first. So we've always worked in the high voltage for automotive is typically around 800 volts.
Right.
So for us to go to 1400 volts, that also comes with its own unique challenges. A lot of the components within the battery needs to the contactors, the resistors, the fuses, all of those things, and also our power electronics as well, all need to be rated for that higher voltage. But we then sort of, if we go back again to cell to module, and then effectively packaging those modules in the most efficient space within this. We call these a subpack because effectively we need 8 of these. These are 185 kilowatt hours each, so typically sort of 3 times larger than a car battery, and we need 8 of these together to get us that 1400 volts and to get us that full amount of energy.
So in terms of you're effectively retrofitting this,
Correct,
into a diesel electric mining truck.
yes.
What power rating do those motors use? What kind of power do we need to develop in this pack
Yep.
to drive those motors?
So the maximum power is 1.6 megawatts, and that would be drawn when it's fully laden, going up a steep incline, probably maximum about 10% is what they use in the mining sites. We've got some very high technology cells working in here. We're able to increase the C rate of the cells, so we're able to really draw maximum power out of the cells when we need to. But typically the motors wouldn't be pulling more than sort of maybe 800 kilowatts to 1 megawatt typically.
So you're pushing the cells using your newest technology, which we heard about a couple of weeks ago on the channel.
Yes.
The high current application is always a challenge for battery packs because high current means you're going to produce more heat within the battery pack.
Yep.
You're going to have higher internal resistances. You're going to have more energy loss, less efficiency.
Mm-hmm.
How do you make sure that something this big, stacked 3 high, is going to remain cool and calm and collected when being pushed in a mining application in somewhere like Australia, where the daytime temperatures outside can reach 40 degrees Celsius or higher, and the temperature and the humidity in mines can be devastating to your normal run-of-the-mill vehicle?
Very much so. So environmental is massive. These are going up to the Pilbara, and you mentioned 40 degrees. Well, actually the Pilbara sees anything up to 50 degrees. So we've designed these to work sort of around the 55, even 60 degrees C ambient temperature. So that's the maximum temperature that they could see. And that again starts back in the digital environment. We've got a number of very clever engineers upstairs that are sort of working in the digital space. They're able to map out all the thermal efficiencies of the design, and we work with some partners around which is the best coolant to use. Again, that's born from our motorsport heritage, pulling all of that expertise in. And we end up with a design here that every module is individually cooled. We have the most efficient heat transfer path to that cell that we can deliver. We ensure that there's no pressure drops or anything that can reduce that efficiency. We do that with CFD and thermal capabilities that we've got here. Again, going back to the motorsport heritage. And ultimately, we're able to do a sort of giant cooling package, which is what this is. Each, as I said before, each module is individually cooled. They're then connected in series through to a chiller unit that we've got at the front, and we actually have obviously the radiator which we're still using from the original truck to sort of draw from that. It's not just the batteries that need cooling though. We have a DC-DC that goes from 1400 volts to 700 volts. That powers the ancillaries, so the ancillary motors for the blower motor, which is blowing cold air or blowing air effectively into the motors. We have the hydraulic pumps as well, which are doing the steering and the braking. And again, those need to be cooled as well. So it's quite a complex cooling system across the truck. And we're also using multiple cooling fluids. So for the batteries, for safety reasons, we're always using dielectric fluid. So if there is a leak, it doesn't affect the isolation performance of the subpack. But where that's less of an issue, we'll be using water glycol circuits to increase the efficiency.
You mentioned there that obviously you've got a very high operating voltage in the truck, and that's because of its previous drivetrain setup.
Correct.
But there are some advantages, aren't there, to having a higher voltage setup that has a lower current, because for a given power output, it's just practically easier to design something that operates at twice the voltage and half the current. And I'm guessing that played a part in this packaging here.
It does. We had to work with as you mentioned before, the inverter motor setup that's already in the truck. We didn't want to sort of change any of that. And part of the reason for that is it's also its braking system. So typically when the diesel engine's fitted, to brake the truck, effectively what happens is the energy comes back through the inverter and gets sort of burnt off as heat energy through a giant resistor grid. We want to try and capture that energy.
Wow, that just blown my mind.
So yeah, it's a very big unit, probably 2 or 3 times the size of this subpack you're looking at now. And all of that energy, you're trying to stop a 400-ton mining truck doing 60 kilometers an hour. That's a huge amount of energy to come through. So it comes through a giant resistor grid. What we want to do is to tap that energy out of that resistor grid and to use it to recharge our subpacks. And that's something that we've done a lot in the testing phase. And we plan, when we put it onto the truck, to test it in the real world as well, to hopefully demonstrate that that's possible.
Wow, the amount of energy and heat that must be generated from regenerative braking something that large and just turning it into heat energy. I guess they must have a massive radiator to cool that as well.
Yes, yeah, big air fans effectively to keep that going. To
keep the temperature down. Now, charging something like this is no mean feat. I mean, it's a massive amount of power stored electrochemically in the battery pack, a massive amount of power that you need to send to the wheels, but also when it comes to external charging, you're going to be working with a fairly new charging standard, right?
Correct. Yeah, so one of the things when you think about this isn't just demonstrating that it's physically possible to put a battery in a mining truck and move it along. That's never been, the outset of this project. It's basically to demonstrate that it's possible to use this in not just the mining environment, but actually it will be a usable asset within the mining environment. And by that we mean it can effectively haul iron ore consistently throughout the day. So it's not sat on charge for half of the day or whatever.
Right.
It's able to do its job for a lot. It has very little downtime. And so very early outset, charging was a really big thing for us. It's lots of things with charging that we had to consider. One is effectively using the most optimal cell, so that we can push all that energy into the cell at the fastest rate possible. And we do that through a number of means. One is through a lot of our electronics and our battery management system, able to control that very, very accurately. Also by having a very efficient cooling system. So obviously the faster you charge it, the hotter the subpack will get. So being able to draw that heat out is really important, enables you to sort of charge them faster. But ultimately, we can't use things like the CCS2 connectors, which are around for the automotive space, because they're just not capable. They're limited in their voltage,
right.
And also limited in their current flow. So we're working with a company who effectively are adopting the MCS charging protocol.
Right,
so that's the megawatt charging system.
The one that looks a little bit like a
it's a sort of bit like a diamond
Yeah.
kind of,
Yeah.
or sorry, triangle sort of shape.
Yeah.
And again, it's not something that you can just sort of, one of you or two of you could just plug in. It's a liquid cooled cable and of a quite a substantial diameter. And we're actually going to be using a robotized arm that'll come into the side of the truck and will connect to the truck. We're working with the protocol and the software to make sure that our system at the moment sort of works with CCS2 and lots of other charging protocols that we've used in the past. This is the first time we've worked with the MCS connector protocol, and I've actually got a team in Australia at the moment, just in their very first infancy with the charging company, trying to work out how all that's going to work. And it's going to be very challenging. It's not just the cooling, it's not just the connector that's actually cooled, it's the mating box as well that it fits into also needs to be cooled. So we need to ensure, obviously safety is the number one priority, but efficiency and performance is our next priority as well. So it's challenging to work in this space, but with all the different experiences we've got around us through all the other automotive, motorsport applications, this is very well suited for us, and I'm sure we'll work through any challenges that we get in the next few weeks.
Finishing off, obviously it's not something that you would necessarily classify as a limited production, although right now it is.
Sure.
Because you're still in those early stages of testing. But looking forwards, there are hundreds of mines around the world that could all make use of this technology, that could all make use of these packs and these sub-packs and assembling them and putting them into existing vehicles. I mean, it's perfect because you're upcycling the actual bodies of the trucks, the chassis of the trucks, which have 20-ish year lifespans. You're putting these battery packs in, but how much over-engineering has to go into building something like this in an industrial application to ensure it has an incredibly long lifespan? Because you're not going to be treating this like you would treat, a standard hatchback EV with a 10-year shelf life. This is going to need to pay for itself maybe in 10 years, but then continue to run for another 10 or 20 after that.
So the first point is to mention here that this is for our one-off prototype.
Yes, of course.
So you could argue we've over-engineered this slightly, but this has to take the weight of two additional sub-packs on top of it. It also has to take the structural loads within the truck. It's the first time we're working in this space, so we've gone sort of belt and braces on the design, big design factors on here, just to make sure that it is absolutely bulletproof. We are working on the next generation of batteries, and there will be a lot more higher volume sort of manufacture. So we'll change the manufacturing methods that we use, but ultimately they still have to be just as strong and everything else within the environment. With regards to sort of fitting into trucks, we do have like a modular approach to everything we're doing. So when if you're able to take the lid off this, you'd see that we have a very sort of modular approach. All the modules are exactly the same underneath here. They're very quick to assemble, very quick to sort of put together and connect. And that's something we'll be taking on to the next generation as well. But most importantly as well, that we're working with FMG to effectively take their whole mining fleet and decarbonise their mining trucks with these. But it's not just the trucks. The plan is to then use these sub-packs across a wide range of other vehicles that are currently diesel today, but need to be decarbonised by 2030 in line with their strategy. So we are working with excavators and dozers and wheel graders and water bowsers and things like that. All sorts of different vehicles will be hopefully adopting these kind of modular batteries. And then once these have got to the sort of limit of their use, if you like, after, once the state of charge starts to drop, below sort of 80-70%, then we start thinking about using these either as sub-packs or taking the modules out themselves and using them in second life. And second life will probably be around battery storage, going to need large amounts of battery storage, because all of the energy that's needed to power these effectively is going to have to come from a green source. Otherwise, it's a wasted journey unless we're actually powering this with green energy. And where we'd be using wind and solar typically up at the mine site to generate that energy, we do need that backup of a sort of battery storage. And we're going to be designing the sort of secondary storage. We'll be using these modules. So that's another exciting part of this journey. And then just to wrap it all up at the end, when they sort of finish their usable life in secondary storage, we're already starting the exploratory works about how we can recycle a lot of the lithium, and we're hoping to get sort of 90% plus
Cool.
recyclability back into our supply chain, and then it all starts again, to effectively design the next generation. So it's a very exciting space at the moment. It's consistently moving along.
And I don't know if you're able to say this, but I'm assuming this is an NCM type chemistry.
Yes, it is. Yeah, you can probably work it out based on the size and number of cells and things like that. But we don't like to talk about the chemistry or the cell manufacturer, because that's quite proprietary for us about how we manage that and the C ratings and things like that. But we are using that sort of around that.
So you're not using any exotic new chemistries?
Not exotic, no. We're always working with the suppliers of the cells, because they like working with us, because we always stretch the limits of their cell capability.
Here, break this.
And typically, if they're selling that product out in the market at a particular C rate, we would go away, take that cell, do a whole raft of testing. They trust us because of our history and heritage, and they would then turn and we'd say to them, look, we've tested at this level. We think the cell could work it quite happily at this operation level. Would you be happy to sort of guarantee your cell at that range? And most of the time, the cell manufacturers are happy for us to sort of stretch the limits of their cells. And again, that goes back to not just our testing capability and the engineers upstairs, but very much around the way that we manage the battery throughout its life through our battery management system and cell management units. They're consistently measuring the temperature and voltage, and again, not just for one pack, but for 8, and then how to manage those as a sort of system. All of that data is then getting fed back to either the team here or into the cloud, where they'll be analysing the data and trying to maximise the performance of the pack.
Fantastic. Thank you so much for chatting with me, Alec. I hope that this project is thoroughly successful and that you all learn a whole lot about this initial first vehicle and can use that all to refine and improve the technology for everyone moving forwards.
Thanks very much. Cheers.
And thank you at home for watching. And on that note, we are done with today's video. If you have comments, drop us a polite note in the Discord chat room on Mastodon, or if you are a Patreon supporter, in the comments there. If you want more, subscribe, hit the bell, and follow the links below to regularly support us with a YouTube membership or a Patreon channel subscription. You'll also find links below to our Ko-fi, Bitcoin and Swag store, as well as that aforementioned Mastodon server. Scrolling on my right is the list of amazing charged up supporters, and shout outs go out to our self-driving tier supporters. They are Paul Nelson, Mike Weeder, Denny Hyde, Linda Irish, Lance Charles, Mark Eggleton, Cyprian Laplace, John Trammell, Alan Tupper, Chris Maxwell, Brian Newton, Bennett Elder, Andrew Martin, Sean Tucker, Pedro Mora Pinheiro, Kyle Hodgson, Tony Moss, Brophy Wolf, Kyle Fox, Hey Esker, Tazla in the Gong, Dan Blair, Peter Dillinger, Gordon C, Stefan Flemgen, Stephen Williams, Regine Fellows, Chris Centaur and Jim Benness. And finally, out of this world, thanks to our top tier supporters, the John L. Henderson, Clay Witt, CPU Freak 101, John Lyons, Kevin Burrowbridge, Andrew Glenn, Joe Hughes, Dave Kitchen, Joe Bresney, Nigel S., Matthew Drobnak, Eric Knack, Paul Conway, Stephen O'Donoghue, JP Fagerback, Reggie Watts, Marcel Ward, Robert Flannery, Aaron Hahn, Rory Litwin, Ellery Hensley, Will Graylin, and of course, Ian. Special thanks also go to WAE Technologies for inviting us here and for covering our board, our lodging and our accommodation. Don't forget that we publish every Monday, Wednesday, Friday and Saturday on this channel. Plus over on Sunday, you hear our chicken and garden update and our Sunday musings over on Transport Evolved Take 2. And with that, I hope you enjoy the rest of your day. I will see you soon, and as always, keep evolving.